Ready to start?
Yes.
Sure. Okay. So good afternoon, everyone. Welcome to this NITheCS mini school on two-dimensional categories by Dr. Elena Caviglia. This is the fourth and final installment of the mini school, so I'm sure our speaker needs no introduction, as you're familiar with already. As always, if you have any questions, feel free to post them in the chat or the Q&A. We will get to them towards the end of the lecture. Please enjoy, and with that, I'd like to hand over to you, Elena. Thank you.
Thank you. So let me share my screen. Okay, so today we are going to talk about limits. So we have spoken about two categories and double categories in the past lectures, and today we are going to see how limits are done in both two categories and double categories. So we start recalling what happens for category. So we saw in the first lecture that for categories, if we have a functor f from D to C, so D is our diagram category, and we want to compute the limit of this functor, the property that we saw for the limit is that we have, for every object A in the category C, we have an isomorphism of category between, we have a bijection between C, A, lim F and this object. That we saw, that we said it's the set of cones. It's done like this. So what are these cones? They are natural transformations, say alpha, between the functor delta 1 and this other functor. So given an object I in the diagram category D, our alpha I goes from the category 1 to C, A, F, I. And so this is the same as having an arrow, let's call it AI, from A to F of I. And this bunch of arrows, one for every I, form what is called the cone. So we have for every I we have an arrow AI, and they form triangles. So now we have, if we have AJ here, and if we have a morphism in I from I to J, we have a commutative triangle like this. So this is the cone. But if you look at this cone, you realize that this is not able to capture two-dimensional, this approach is not able to capture two-dimensional cones. So if I now, instead of just having a bunch of arrows, I also want to have two cells between these arrows. So for example, a two cell between two of these morphisms. I cannot really capture with this kind of cone this phenomenon, so these two cells. So we need to upgrade the cone in order to be able to capture two cells. And there are different ways to do this, but the way in which this is done in enriched category theory is that of introducing what is called a weight. So instead of just having delta 1 here, we will have a more general weight. So we replace delta 1 with a weight. So our weight is a functor W from, so imagine now we are in a two-category L. Our weight W is a functor from L into cat. And so in particular, delta 1 is a special weight. So it's just the functor that sends everything into the category 1. But we can have many of them. So now if we want to compute the limit of a diagram of a functor f from D to L, what we can do is compute the limit of f weighted by this weight W. And so the condition that we have, so our bijection that we had earlier, becomes an equivalence of category between these two categories. So we have L A lim of f weighted by W, and the cat W L of A F. Like this, and this is natural in A. This is precisely what happened earlier, the naturality. So now we don't have delta 1 anymore. We have a generic weight W. So this is much more general. And here we get an isomorphism of categories. So this isomorphism of categories now has two levels. We will have an assignment on objects, and this is the one-dimensional property of the two limit. So this is going to be similar to the usual universal properties of limits that we have in categories. But we also have an assignment on morphisms, and so on two cells. And this is going to give a two-dimensional universal property of the two limit. So every two limit has a one-dimensional universal property and a two-dimensional one. And now, as I was saying, W is very general, so we can have many different kinds of two limits. So maybe we can start seeing a two limit that has a weight that is different from delta 1, just to see that not all of the limits we care about will have delta 1 as weight. So we can consider the comma object, and this is a two-dimensional version of the pullback, and we are going to see why. So this is an example of a two-dimensional limit. So our category to category D, we were writing it in italics, so let's do it. D is the same that we had for the pullback, if you remember. So we just have the two arrows like this. So this is our diagram. But now we have a weight, W. So this weight, W, Oh, sorry, I made a mistake here earlier. So W doesn't go from L here. It goes from D, the diagram, of course. Right. So now our weight W, we'll have to kind of assign a weight to every object in the diagram, in the category diagram D, and then an arrow to every arrow. So how this is for the COM object? So we assign to these two objects the category 1. So they both go to the category 1. But then this other object here goes into the category 2. Right? So what is the category 2 is just the arrow. So 2, we can see it as an arrow from 0 to 1. This is the category 2. So our weight sends D into this to this shape, kind of, okay. And now, so what happens is we want to compute the limit of F. So F will send D into the same shape, but in the two category L. Let's say that the shape is this. So we have F and G, like this. Okay, so this is our F. And what is the weighted limit? So lim of F weighted by W. It's like this. So it's going to be an object. Let's call it P because it's kind of a pullback. So here we have our G and our A, F. So an object P together with two morphisms, one into B and one into A, but also a two cell like this, say alpha inside the square. And this two cell is given by the fact that here we have 2, right? So our weight as a 2 here. So we get a 2 cell inside the square like this, alpha. And then we have that this is a universal such 2 cell, such square. And so what we get is a one-dimensional universal property. And this universal property says that if we now have, we start from a square like this. So we have square like this with here G and here A, F, with a 2 cell inside, say beta. So it's like the universal property of the pullback, but now we take a 2 cell inside, beta. We can construct a morphism, a unique morphism from D into P, our comma, B. So this is our initial square with alpha inside. So there exists a unique arrow from D to P such that this pasting diagram, so we paste this alpha with the unique arrow, or if you want, we can view it equivalently as pasting with these two triangles, but they are commutative, so they have identity 2 cells inside. And this pasting that we get is precisely equal to beta. So our starting 2 cell. So this is the one-dimensional universal property. And then we have a 2-dimensional universal property. So the one-dimensional one is in some sense similar to what we can expect. So it's similar to the universal property of the pullback. And now we have a two-dimensional universal property saying that if we have two arrows, two arrows like this, we get a unit to cell between them. Okay, so we're not going to see it in detail, but trust me, there is a two-dimensional universal property. And so this is how we replace the pullback in two categories. So it's not anymore a commutative square, but we have a two-cell inside. But what happens if we now consider the same limits that we considered for categories, but in this two-dimensional context? So for example, what are products? Okay, products are, or two products, they can be called. So now what happens if you know, we have the same, so our D is just the 2 points, and now our weight is delta 1. So what happens is we get the same thing as a product, so it's still, so suppose that F gives A and B. So the product is still A cross B, together with two maps, one into B and one into A. But now it still has the usual universal property of the product, but it also has a two-dimensional universal property, taking into account the relationship with two cells. And this comes from the fact that we now have an isomorphism of categories. So we have an additional level. So it has the usual universal property plus a two-dimensional universal property. And we can do the same for equalizers. So we get two equalizers. And we know that in dimension 1, all limits can be constructed from products and equalizers. And we can ask whether an analogous result holds for two categories, for two limits. We already know that we cannot construct all two limits starting from two products and two equalizers. And this is because two products and two equalizers have weight delta 1. But we have seen that there are limits that don't have weight delta 1. And so we cannot construct them only using limits with weight delta 1. Limits that have weight delta 1 are usually called conical. So we cannot construct all two limits starting from conical limits. We need to add something more. But what is true is that we can construct all two limits with two products two equalizers and powers. So we need to add powers. And what are these powers? So we are not maybe going to see them in this is quite hard to prove. It's not like a straightforward result, but it has been proved. So what are powers? The idea is that we want to take an object of our two category L, and then we want to take a category C in cat, so. And in this case, we take a category because we are considering cat-enriched cat-enriched categories, so two categories. But more in general, this can be done for all enriched categories, and here we take an object in the base of enrichment. And the power can be seen as powering x to the c. So this is the power. And the property it has is that L of x, okay, maybe let's call it just not to confuse with the notation, let's say L of y x to the c is the same as functors between c and L y x. So this is the property this power has. This is how we define power x to the c. And in cat, so in our first example of two category, powers are functor categories. So it's an object we know. So D to the C is just the functor category from C into D. But more in general, we can define powers for any two categories, and we can construct all two limits using two products, two equalizers and powers. Okay, so we briefly spoke about bicategories. So let me say just quickly what happens when we want to consider limits in a bicategory. So remember here we had this isomorphism of categories between these two categories, and this category on the right is a category of natural transformations. Okay, so what happens for bicategories? We want to weaken both these conditions. So instead of having, so for bicategories, instead of having an isomorphism, we just ask for an equivalence of categories. And instead of considering natural transformations here as cones, we have that cones are pseudo-natural transformations. So we weaken both the condition here and the cones that we can get. And what we have is the notion of bilimit. Bilimits. So we're not going to see this in details, but this is what we get. And of course, we can also consider bilimits for two categories because they are special bicategories, and some bilimits are indeed used. For example, there is a bilimit version of the comma object that is called bicomma object. And sometimes it's useful. And the difference that it has with the comma object is that in the one-dimensional universal property here, we don't have equalities in these two triangles. We don't have identity to cells, but we have an isomorphic to cell. So this is the bi-comma object. And there are many other interesting bi-limits. All right. So now, as promised, we want to also see what happens for double categories. So we move to the world of double categories. So we study limits in double categories. Okay. And last week, because we didn't have enough time, we didn't speak much about functors and transformations between double categories, but a functor between the two double categories, say A and B, is called double functor. And it preserves everything you can imagine. So it preserves all the identities and all the possible compositions of arrows, pro-arrows, and double cells vertically and horizontally. So it preserves everything strictly, double functor. And then we can introduce a notion of horizontal natural transformation. So of course, there is also a vertical version of it. Or if we don't want to use the name horizontal, we could call it an arrow natural transformation. So if we have two double functors f and g from I to a double natural transformation alpha, horizontal natural transformation. So horizontal means it is in the direction of arrows. So it's given by for every I in the domain category I, we have an arrow alpha I from f of I to g of I, so it's the same as the data we have for a natural transformation. So this is an arrow. But then for every pro-arrow, so if we have a pro-arrow in I, let's call it U from I to J, a pro-arrow, we have a double cell associated to it. So it's going to have F of U as domain pro-arrow. It's going to have G of U as codomain pro-arrow. And it's going to be a double cell like this. And we call it alpha U. Okay, so it's associated to U. And these data are such that, so if we consider the identity pro-arrow, alpha of identity is the identity double cell, but also alpha of V composed with U is going to be alpha U alpha V. So we compose the two double cells vertically. And then we have a compatibility with double cells. We don't want to see many details, but it's basically it behaves like a natural transformation in the arrow direction, but in the pro-arrow direction is kind of a pseudo-natural transformation. Right. So now what is a cone in this double categorical context? So if we have F from I to A, so I call the diagram double category I just because D is the usual name for any double category. So we have double functor. We want to compute the limit of this. So what is a double cone for F? Double cone for F is given by these two data. So for every I in I, an arrow AI from from A to F of I, because we are assuming that this cone is on an object A in A. So we get for every AI a morphism this. Now it's not changing to writing mode anymore. Let me refresh. I hope it will work now. Oh no, it's not refreshing it. Hopefully it will do it. But while we, okay, I can see it. While we wait, I was saying that, so for every, what's this? So for every I, we have an arrow from so we have an arrow. I don't use the rubber, otherwise it's not working anymore. So we have an arrow from A to F of I. So these are the arrows that make up our cone. But then we also have a bunch of double cells. So for every row arrow U from I into J, we get a double cell. And this is a double cell of this form. So we have F I. Here we have F J. This is F of U. AI. AJ. So it's inside these cones we have double cells. So this is AU. This is a double cone. And then we have naturality conditions. So double cone is indeed an horizontal natural transformation between the constant double functor in the object A and F. So this is the same as A from D or delta A into F, horizontal natural transformation. Okay, so it's the same idea. So we have this kind of natural transformation, and what it amounts to is a bunch of arrows of this form, but also a bunch of two cells. And then we have naturality conditions plus naturality conditions. And what is the double limit? So the double limit lim of F is now a universal double cone. So is a universal double cone. So lim F corresponds to a natural transformation from dA into F, so it's a cone, plus universal property. So you can maybe imagine how the universal property will look like. We will have a usual universal property involving a factorization of these arrows, but we will also have a double universal property. Okay, we don't have time to go into the details of these, but I want to show you the example of a tabulator, because it's a new kind of limit that we only have in double categories. So what is the tabulator? So the tabulator is a double limit in which our diagram is just a pro-arrow. So we take a single pro-arrow, let's call it, so the diagram is like this. Oh, not again. Oh no, okay, it works. So the diagram is like this. So our double functor F will have as image a pro-arrow in our double categories. Let's say it's like this. It's a pro-arrow U. And what is the tabulator of U? Of U. It's going to be an object. Let's call it TU, together with two morphisms. One into A, we can call it P, and one from TU into B. Let's call it Q, but also a double cell of this form. So here we have U, here we have the vertical identity of TU, and we have a double cell pi of this form. So the tabulator of U is given by the object TU together with the two arrows P and Q and this double cell here, pi. And what are the two universal properties? So this tabulator is such that, so the one that's similar to something that we can imagine says that if we now have another object X with two arrows, one into A and one into B, so this G, and also a double cell in here, let's call it alpha. So for every such alpha, so such X with F, G, and alpha, there is a unique arrow H from X into TU, so an arrow X from X into TU, such that if we now do this arrow H and then we attach it with alpha, sorry, we do arrow H and we attach it with pi, like this, so H pi. This is the same as alpha. So we can somehow factor this double cell alpha with our starting double cell pi, we including an arrow from X to TU. So this is the one-dimensional universal property, let's say. And then there is an additional double universal property that is quite complicated to write down. That is called the tetrahedron property. And you can have a look if you want to the explicit form. But what is interesting is that this new kind of limit, that's the limit of a pro-arrow. So intuitively, in a double category, we can still do all limits that are along arrows in the usual way. We can do products, we can do equalizers and so on. But then we also have limits that involve the pro-arrow's direction. And the simplest limit involving the pro-arrow direction that we can imagine is indeed the tabulator, because we just take as diagram a pro-arrow. And the interesting thing is that also for double category, we have a theorem about constructing limits from simple ones. And it says that all double limits can be constructed from products equalizers and tabulators. So this is saying that this simple pro-arrow limit that we are considering is enough to construct all pro-arrow limits and all mixed limits together with products and coequalizers. And this result to me is very interesting. And in general, all these results of construction of limits starting from simple ones are quite interesting to me, because they tell us how these two-dimensional limits behave, and how we can construct all of them, starting also from limits that we know from ordinary category theory. And this is everything I wanted to say, so you're welcome to ask any questions, and thank you very much for joining the mini school.
Thank you, Elena. That was great. I see there are no questions in the chat or in the Q&A, so I guess we can open it up to if anyone has a question they want to ask live, then you can raise your hand and we'll give you the chance to speak and ask your question. It didn't seem like there's any questions. I take it that everyone is happy then, or still processing everything. But I'm sure afterwards, if you would like to get in touch with Elena at a later stage, then I'm sure you'll be able to do that or get through the NITheCS channels to ask your questions. But other than that, I hope that you've all enjoyed this mini school, not just this episode, but all of them so far. And thank you again to Elena for hosting nice month-long mini school. It was very nice. Thank you for that. Yeah, I guess we can leave it here then.
Thank you.
Thank
Goodbye.
you. Bye, everyone.